Hello everyone. I would like to thank you before starting my presentation for your for attending to it. My name is Franco Falconi, and today I will present you my work on the control strategy for the combustion optimization for waste to energy incineration plants. So this work has been done in collaboration with Schneider Electric and the Conservatoire National des Arts et Métiers in Paris, France. To do so, I propose you the following agenda. So first of all, I will make an introduction and a problem statement of what incineration plants are for. Then I will propose to you a model of the combustion of this process. Then we will go through a control strategy for the optimization of the combustion, and finally I will conclude on this work. So as we can see here, the quantity of municipal solid waste worldwide is increasing, given that we are consuming more and more um, we're consuming more and more objects, and so we are producing also more and more waste. So we need to take we need to dispose of this waste, and there are several ways of doing so. One is to put this on landfills, but this will cause a lot of pollution. And another solution that could, uh, let's say, give a good balance between pollution and space is using incineration plants. So, as we can see, given that the population is constantly increasing, so this is just to show the population of the United States, but the world population is having the same curve and the same tendency to increase. So we need to have solutions in order to cope with all this new waste that will continue to appear. And so to do so, we have this already existing solution that is called a waste to energy incineration plant. So how does it work? So first of all, we have the waste from houses that is collected by trucks. Then it arrives to a pit where we have a big mechanical crane that will take all this waste and will put it into the grate, as we can see here. So this waste is then burned, and the energy of the smoke that comes from this combustion is then given to a water exchanger that will produce steam, and this steam will go through a turbine engine in order to create electricity. And also, in some type of plants, we have cogeneration, which means that the remaining energy that is contained in the steam will be given to the municipal heating system. So in our case, we're going to focus on the combustion, the control of the combustion. So we want to make the full automation of the combustion process, but there are some problems. The first one is that for a classical PID control, this kind of process is way too complex to handle. And also, we need a real-time computation of the command, which means that we cannot use very complex, for instance, CFD, so computational fluid dynamics, in order to model this kind of process. So the solution is to try to obtain a simple and reliable model of the combustion of this waste in order to control the steam production. So just to have some figures on mind, currently the set point is to produce 125 tons per hour of steam. The process average value is 122 tons per hour, with a standard deviation between 7 and 11 tons per hour, which means that we have a process that has a big variability and is not well controlled. In order to have a combustion, we need obviously three main ingredients, which are the fuel. In our case, is the municipal solid waste. We need the oxygen that is given by primary and secondary air. So primary and secondary air are basically just air that is taken from the atmosphere, so from ambient air, and it's sent into the combustion chamber in order to give all the needed oxygen for the combustion. And finally, the heat that will maintain the combustion um, is given by the flame that already exists, which means that this combustion is self if uses its own energy in order to continue burning. So here is a table of some values and composition of the municipal solid waste. Um, so just to give you some ideas, the low heating value, LHV, means the energy that is released by the combustion of 1 kilogram of dry waste, which is the value that we will use for our modeling. And the air stoichiometric ratio is simply the quantity of air that you need in order to burn 1 kilogram of waste, which means that if I want to burn 1 kilogram of waste, I need 3.9 cubic meters of air. So how does the grate works? So at the beginning of the grate, we have the injection of waste. So we can consider that we have an homogeneous waste bed. Then this waste bed will start burning as it goes through the flame, and at the end of the grate, we will just have the clinker, which is the remaining of the combustion that cannot burn. So it's mainly composed of metals and inert material that cannot burn, obviously. So in order to model this, the first part of the grate will be just modeled as a classical um, integrating system, which means that we have the change in the height of the waste bed will be due to the speed at which the waste bed leaves the first zone and the quantity of waste that we introduce into this waste into this waste bed, obviously. And secondly, the combustion zone will be modeled obviously by the variation of the height in this combustion zone will be linked to the quantity of air that is introduced in order to burn the waste, because the more air we introduce, the greater the quantity of waste that will be burned is. And in this case, we have this equation, which comes from a balance of mass. And for the energy balance, so uh, we need to make an energy balance in order to estimate the temperature in the combustion chamber. And to do so, we are going yep, sorry we're going to consider that the energy change is due to the combustion, the radiative heat transfer, the energy loss in the heating of the air that wasn't used for the combustion, and the inerts. So, oh, sorry, yeah, I don't know why it's yeah, okay. So for the combustion energy, we have we are going to consider this virtual transformation in order to evaluate the total energy released by the combustion. I don't know why it's okay. Yep. So then, in order to evaluate each step of the virtual transformation, we have the first step, which is taking all the fuel and bring it to the standard conditions. Then we have the energy release at standard conditions, and finally we have to take all the products of the combustion to the final state, which is the last line, and we have a minus sign because we are considering an exothermic reaction. Um, then we have the air that wasn't used to the combustion, but it's used um, uh, to cool the combustion chamber, which is the suppressed air. And we also have the energy that has been received by the inerts, because the inerts at the end of the combustion have a certain temperature, so they have received a certain energy. And finally, we have to take into account the energy that has been lost by these hot gases, because they are obviously radiating with and they follow the Stefan Boltzmann law of radiation that we can see here. Um, yeah, sorry, that we can see here, and this fact is the main fact of which the gas gives the energy to to the water that will evaporate. And finally, once we have this combustion chamber temperature, we need to make the link between the temperature and the steam. And in order to do that, we decided to use a simple regression equation between the steam and the arc temperature. So let me show you some results of this simulation. So here you have in black, so the simulated, sorry, in red, the simulated value with the model, and in black, it's the real actual value of the industrial process that has been taken from a real combustion incineration process. So uh, what is really interesting to see is more the here the error. So we can see that we have a mean error of 3% with a standard deviation of 2%, which shows that 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 the let's say this simple model can really take into account all the some variations of the real process. And if we see the steam production, here we can also see that with the error we have a mean error of 3% with a standard deviation of 3%, which means that also here the process and the model have the same have a very good um, uh, let's say uh, are really close. So this big spike on the error is due to the fact that this big spike is in fact a problem that with the incinerator when there wasn't a good combustion, and we have a big drop on the temperature, as we can see here. And this big drop on temperature influences obviously a drop in the steam. In order to do the control strategy, we're going to control. We have three state vectors for the modeling. We have the height of the homogeneous waste of bed. We have the height of the bed at the end of the combustion, and the temperature of the gases in the arch. For the outputs, our outputs are the variables we want to control. So we want to control both heights at the beginning and at the end of the combustion, and the steam flow rate. And to do so, we have the following actuators. We have the feed rate of waste, the primary air for the combustion, and the surplus air in order to keep a certain temperature of the combustion chamber. So we have our nonlinear model that comes from all the equations that we have seen previously. And what we are going to do is we're going to linearize around an equilibrium point, this nonlinear model, in order to obtain linear representation to apply uh, a linear quadratic controller. To do so, we are going obviously to to create the augmented system in order to add the integral state feedback. And once we've done this by using these equations, we can perform the linear quadratic regulator. And here we can see a simulation in which we created a drop in the steam production of 10 tons per hour, as we can see on the left hand side. And on the right hand side, we can see both actions. So first of all, we have the primary air that rises. So this is in order to burn more waste. So when your primary air goes up, you are basically burning more waste because you are adding more air to the system, so that the system can use more oxygen to burn more waste. And on the same time, the high pressure air, which is the pressure air in order to maintain the combustion chamber within a certain temperature, also drops. So what we are doing is that we are um, burning more waste and cooling less, sorry, the combustion chamber, in order to have a bigger temperature to compensate this disturbance on the steam flow rate. So in this work, we have presented a model that can describe accurately the process of combustion in an incineration plant. Also, we have presented a control strategy that has yet to be tested in a real incineration plant. Um, there is also some issues which are related to the evaluation in real time of the low heating value. As I said before, the low heating value is the energy released by the combustion of the waste bed. So we have this mean value, but the problem is that uh, this value has a lot of standard deviation. So we need to try to evaluate it beforehand in order to have, let's say, a consistent control strategy. And finally, we need to compare this proposed control strategy with other existing control strategies that have already been implemented on this type of assets and process. So thank you very much for your attention.